Hi, what's up? How's it going? So today we are going to be talking about question 1 from the quiz 6 review sheet, just kind of going through the store word instruction and how that gets executed on the CPU. So I guess the first thing to just talk about here is like, what does the store word instruction actually do? Because if we know what it does, then we can kind of go through and trace everything that's happening on the CPU. So the store word instruction is basically saying like, I have some value in S0, right? Let's say that I have like this value, let's say it's 4, and I'm storing the value of 4 in S0. And so I want to take this value, like 4 in S0, and I want to put it deep into memory somewhere, like into my data memory. And so that is what the store word instruction does. So a way of thinking about it is it's doing something like memory. So in this case, we'd say like memory of T0 plus 4 is equal to S0. And so this is kind of like going into memory and it's saying whatever this address is, so T0 is going to be some address, and we know that T0 is holding an address if we're using this instruction. And then we're going to have some offset, and I'll talk about the offset in a second. And we're going to basically go into this place in memory, and we're going to set that part in memory equal to S0. So it's like the opposite of load word, right? With load word, we're taking a value from memory and we're putting it into S0. And here we're taking whatever value is in S0 and we're storing it in memory, which is why it's called store word, because we're storing this word in memory. And so all that's going on with the offset is that if T0 has some address, then, so let's say that T0 is like some address here, some hex number pointing to some place in memory. We're going to say, okay, here's my T0, and then the offset is 4 in this case. So, okay, 1 byte, 2 byte, 3 bytes, and 4 bytes. And so there's kind of our offset. And then we're going to say, okay, now take our S0 and store it into these next 4 bytes here. Because it's a store word. And so word is 4 bytes. So that's kind of why we're taking up the next 4 bytes. And then we also have this offset of 4 here. And you don't need an offset. You don't need an offset. I mean, you could have just said like T0 equals T0 plus 4 or something in the first place. Then you wouldn't have even needed an offset. But I'm just like kind of doing it for the point of this example to illustrate what the offset is doing. So, okay, so now we kind of know what our store word is doing. It's taking this value that is stored in S0, and then it is storing that in memory. So that's kind of what's going on with the instruction. And then so how do we actually apply this to the CPU? So the way that the store word instruction is written, when you write it out in machine code, it looks something like this. So this is like our opcode. So that is where our opcode is going to be stored. And then this part here is going to be the source of the memory address. So this corresponds to basically T0. So like what register? We're basically indicating like what register holds our memory address that we want to store something in. And then this part right here is like the source of our data. So where like, you know, this number 4 or whatever that we want to store in memory, what register is that coming from? So that's coming from S0. So like this is like, you know, S0, this is T0, and then here is our offset. And so this is like a 16-bit value that just holds our offset. So in this case, our offset is 4. So we have like 4 here. And then the kind of number that corresponds to register S0 is 16. And then the number that corresponds to register T0 is 8. And that's just like something that you would have to memorize or look up in a table or whatever to kind of know that. And then you also have your opcode for store word. So when the CPU is like, which is kind of reading through the instructions, right? You have the program counter that is like pointing to instructions in memory, and when it gets to this place, like it somehow needs to split up this instruction into different segments and kind of do stuff based on that. So okay, let's like kind of look at then what happens when we get this instruction. So the program counter, let's say that we are starting like. So, okay, let's say that we're like kind of starting here. Okay, so the first thing, I mean, you know, we're going to do something in instruction memory, but we're also just going to increment our program counter by 4. And so then that'll kind of come back around here. And so that's just our basic like incrementing program counter by 4. So that way we can, you know, start move to our next instruction that will be executed after this on the next rising clock edge. So, okay, so that's like that. And then as far as the instruction memory, so the program counter has stores an address to some instruction in memory, and we're basically just going to get this instruction out. So we're feeding our program counter into the instruction memory to actually get our instruction from the address that the program counter was pointing to. And in this case, our instruction is like the 32 bits that we just talked about. So, you know, it's these 32 bits in the same format like this. This is the instruction that we're going to have at that point. So then we have to like kind of split this instruction up. So like I have these kind of these like indicators here, which is kind of like indexing out the bits of the instruction. And so that's like what we're using in this diagram. So at the point that we are now with this little green point, we're saying like now the CPU has access to this instruction because the program counter was pointing to some like memory address that was holding that. And so we now have access to this instruction because we got it from instruction memory. Okay, so now how can we like divide this instruction up to do what we want to do? Okay, so the first thing that we need to do is actually get the values from our registers, right? So let's say that we had the instruction, for example, like store word, you know, S0, 0, T0. So the first thing we need to do here is kind of get the values that are stored in S0 and in T0. Okay, so then looking at our diagram, we can see that S0 corresponds, so like right here, S0 corresponds to bits 20 through 16. Okay, so if we kind of trace through this, then we say, okay, we're going through here, and this, and this is going to be basically this is kind of saying like, take in an address and give it to a register file, and then our register file will spit out whatever value is at S0. So we're going to go through here, and then we know that this value that's coming out of here is going to be the value that's stored at S0. And so that's kind of what the job of the register file in general, right? We give it an address to some register in the file, and then it spits out the value of the register. Okay, so that's going to give us S0. And then we also know that bits 25 through 21, like down here, they correspond to T0. And T0 is actually where we're kind of trying to go in memory. So T0 is probably going to be like some hexadecimal, like, I mean, it'll be in binary, but like, you know, some address that corresponds to a place in memory. So then we go here, and we say, okay, here is our address to T0, and this will give us the value that's stored in T0. Okay, so now we have the address. So this is kind of like the memory address that we want to store to. Memory address that we want to store to. Here is the value that we want to put in that memory address. And then we also have to take into account our offset, right? And our offset is stored in the last 16 bits, or bits 15 through 0 right here. And so we're going to go through here. And now we have our offset coming out of here, which I think I said in this example is 4. And so, okay, then what do we do with our offset? So we want to take our memory address, right? And we want to add the offset to that, which means that I basically want to feed my offset up through here. And then I want to add this to T0. So my offset is going through here, and I want to add this to whatever value is at T0. So then this is going to kind of come out of the ALU, and this is kind of our like T0 plus 4, which is exactly what we wanted. So now we have that, and so now we can just feed this into the address that we wanted to write to, right? Because now we're saying like, okay, I know that I have this address that I want to write to, and my address is going to be T0 plus 4. And then the question is like, what do we actually want to write there? Well, we want to write the value that was stored in S0, right? So like if the value was like, I don't know, 4 or 10 or whatever was stored in S0, we want to write that to that address. So then we go here and we, let me use a different color. And we're saying that we're kind of tracing down through here. And then this is what our write data is. So this is what we actually want to write to that address. So, okay, now we have our address and we have the data we want to write to it. The only other thing is we have to make sure that we have our write enable here. It's equal to 1. Yeah, and then we're done, right? Because all we wanted to do here was we wanted to say, take the value that was in S0 and write this to memory, right? Because we were saying like memory of, in this case, like T0 plus 4 is equal to S0. And so you could think of it as like indexing your memory. And that's equal to whatever value is in S0. Okay, so now we kind of like know everything going on in our CPU, and let's kind of translate that into values coming out of this like control unit. So, okay, register write. So are we writing to any registers? No, we're just reading from registers. So register write is going to be a 0 for the store word instruction. Okay, what about register destination? So what is register destination control? Okay, well, if we trace through here, right, register destination, and then we go here, like what is the output kind of controlling? So the output is controlling the address of a register file that we write to. So are we writing to any register files in this example? No, right? We're just reading from register files. We're not, and when we're writing to memory, but we're not actually writing to any register files. That would be something if I had like, I don't know, add like T4, T5, T6, then we basically add these together and write that into there. But so then, you'd have to worry about where we kind of what address in the register file are we writing to. But here we don't have to worry about that because we're not writing back to any registers. So it's kind of a moot point. It doesn't matter. So you can just put like an X here or something because it doesn't matter what our register destination is. Okay, and then as far as our ALU source goes, well, what is our ALU source controlling? Okay, kind of tracing through this. Our ALU source is basically controlling what gets fed to our ALU. And so in this case, what are we feeding to our ALU? Well, we're feeding this like green line. So you can like follow this green line, which is this like one, I guess like kind of the second value in the mux, or like one because we have 0 and 1, which means that I want to put a 1 here, right? Because we're saying like basically grab the value that's stored in the next one in the mux and feed it into the ALU. So we know that our ALU source has to be 1. Okay, and then what about our ALU control? So this kind of just controls, what is the ALU doing? Is it adding? Is it subtracting? In this case, we're just adding because we're saying like T0 plus 4. So our ALU control should be 0, 0 based on the chart that was given to in the problem. I think it says 0, 0 is adding. And then, okay, what about branch? Or, I mean, are we even doing any branching here? So like, no, we don't have to worry about branch, but also like you can kind of, I'll put a 0 here, but you can kind of see like why, we're not even doing anything with this path or anything. We're not doing anything up here. And also if you kind of trace where this goes to, ultimately we want a 0 on this line. So that way, when we increment our program counter, we're just getting this kind of green line down here, which is just PC plus 4. So we want a 0 coming out of here to select that. And then if we want a 0 coming out of there, that means that we need a 0 on this AND gate to kind of do that. So that's where that branch is coming from. And then, so, okay, what about memory write? So are we writing to memory here? Yes, we are writing to memory. So, with that logic, you could say, okay, well, we're writing to memory, so it's a 1. But kind of to see why we need that to be a 1, it's just because memory write is connected to WE, which is like write enable. So it's saying, I want to actually enable writing to memory. So on my data memory, which is why that needs to be a 1. And then we also have mem to reg. And so let's see, what is that controlling? So if we trace through this whole line here, this is basically controlling the output of this mux. And then, okay, well, what does the output of this mux do? So we go down here, and this mux is just basically writing to our, it's basically specifying the value that we write to a register file, right? So if we were writing back to a register file, you would need the address to write to, and then you would also need the value. And so this is saying like, what value do we want to write back? And in this case, we don't care because we're not even writing back to our like register file, so it doesn't matter. So mem to reg then is just like an X because we don't care what that value is. And I think that should take care of everything that we need. So if you want to go back and fill out the table with kind of what we talked about, we said, okay, register write was a 0 because we weren't writing to any registers. Register destination doesn't matter because we are not, again, like we're not writing back in the write back stage, so it doesn't matter what the register destination is. The ALU source is 1, just because like, again, we're selecting what we're feeding to our ALU. The branch is 0 because we're not branching at all. Mem write is 1 because we are writing to memory. Mem to reg, it doesn't matter because we're not doing anything in the write back stage here. And then ALU op is just 0, 0 because we're adding the offset to the value stored in T0. And yeah, so that's pretty much the overview of what's going on in the store word instruction. There's a few things going on there, but like the point is that you can kind of methodically analyze any instruction just by tracing through the different kind of values coming out of the control unit and see like what mux are they controlling? Is this relevant to the instruction I'm doing? And kind of how can I feed this, like how can I kind of trace through this path and feed whatever values in I need as like outputs and inputs to wherever they need to go. Yeah, so I don't know, hopefully that was helpful. I gave you a sense of the single cycle CPU. And yeah, good luck on the last quiz.